Now we'll talk about cosets, and let's give a definition. Let H be a subgroup of a group G, then the subset A H like this. And again, sometimes you might want to put your binary operation here, is equal to AH such that H is in the subgroup for A in the group G. So the set generated by this, so for example, you pick a member of the group G and you multiply by all the members of H. If you multiply on the left, this is called it is the left coset of H containing A. That's a definition. So if you multiply all the members of your subgroup H on the left by a member of G, that's the left coset of H containing A. And then for the right coset, again for A in G, is the right coset of H containing A. So we have these left cosets and right cosets. Again, notice that A comes from G. And now one thing important to note the cosets will not necessarily be subgroups. They might be in some cases, but not necessarily so. And something else very important as well, note the cosets will partition the group. And what I mean by that, if you make cosets, let me say it this way. If you create, say, left cosets Or the same thing if you made rate cosets. Using each member of G, then the cosets will partition the group G. And you remember what a partition is? It's a group of sets such that the intersection of any two of the groups is the empty set, but yet all the members of the sets together make up the group G. And let's do an example. So let's consider a piece of paper under here. Let's do this example. Find all the cosets, and I'll use like say left cosets of the subgroup generated by 2. Remember, we use this notation to represent the cyclic group generated by 2 of Z12. So let's take a look at this. So again, what we have in this case, our group G is Z12. And then H, the subgroup we're considering, is this one here, 2. And remember, 2 generates, if we keep adding 2's together, and if you have like 2, then 2 plus 2 is 4. 2 plus 4 is 6. 2 plus 6 is 8. 2 plus 8 is 10. Now, then if 2 plus 10 is 12, we go back to 0 and start all over again. So the cyclic subgroup created or generated by 2 will be this group here. So that's going to be our H. So now let's make the cosets. And so we'll take each element of Z12. And you remember what Z12 is? It's going to be 0, 1, 2, 3, up to 11. So we'll take each of the numbers here. So the first one, if we add 0 to our subgroup, again, we're assuming addition is the binary operation. Then we do that, we're just going to get our subgroup back, of course. And what if we add 1? So I'm adding 1 to all the elements. Now notice we can probably stop right here because look, these 2 cosets have partitioned the group because again, all the elements of Z12 are in one of these subgroups, or excuse me, in one of these cosets, And so we could actually stop here. But if we didn't notice that and continued and tried to go on, let's say if we did go on and we didn't notice that, so let's take 2 out of Z and add it to this one. That's going to give us 2, 4, 6, 8, 10. In other words, I'm going back to our original subgroup and adding 2 to each one. And then the next one's going to be 12, but 12 is going to be 0. So notice this is the same. And let's say if we added 3 to our original, we have 3, 5, 7, 9, 11, and then we add 3 to this one, we get 13. And of course, 13 mod 12 is 1. So that's going to be the same as well. Again, they're just in a different order. So these are the same, and these are the same. So then the cosets are just these two that are different. Again, they could have been generated by this or this. And again, if you continue on putting other numbers, once you realize that you have a partition, then any of the others will just create repeated cosets. So the cosets are this and this one. So those are the cosets. And again, sometimes the left coset is different from the right coset, but in this case, if we would have done left cosets, excuse me, we did left cosets, we would have done right cosets. Since it's just addition, and addition is cumulative, we would have gotten the same thing. Now, again, sometimes you'll get something different if you do a right coset compared to left coset, so be aware that, but in this case, we would not get something different. But even if we did get something different, the left cosets would also partition the group. So let's take a look at this problem here and find the cosets of mu1 in the group S3. And so let's find, this time let's find both the left and the right. So let's take a look at this. So when this is the group G, in our context, this would be the group G. And then H is going to be the cyclic subgroup generated by this. And of course, remember what you do to create a cyclic subgroup. You would take the first one, and then the first one times itself. And we'll look at our little chart to see what that gives us. So if we take mu1 times mu1, we go rho naught. And actually, that's the identity. So we can actually stop right there. because once you get to the identity, we'll end up just repeating after that. So we get mu1 rho naught like this. So now we want to find all the cosets. So let's go through and do that. And so the cosets, we want to do the left cosets. So that means we're going to take each one of these, multiply by our subgroup H. And again, we multiply them on the left. So rho naught. Of course, rho naught is the identity. So we're just going to get the set itself back. And then we're going to go to the next one, row 1. Again, we can stop whenever we see that we get the whole original group partitioned. Now, row 1 multiplied by mu1, we're going to have to look at our chart. Row 1 times mu1 is mu3. And of course, this is the identity. So row 1 times the identity is going to be row 1. And then over here, row 2. We're going to have to look at our table again here. And row 2 times mu1. Row 2 mu1 is mu2. And of course, row 2 times the identity is going to be row 2. And, well, actually, we've already partitioned the original group, haven't we? Because we got all the members of the original group in our cosets. Mu1, mu2, mu3, row naught, row 1, row 2. So if we did more of them, we would just get repeats. Let me just give you an example. If we did, let's say if we went to the next one here, mu1 times our subgroup here, if you look at our little chart here, mu1 times mu1 is the identity. And of course, mu1 times the identity is going to be mu1. And you see that's a duplicate. That's a repeat. So we can kind of get rid of that because it's a repeat. And again, we would get repeats the rest of the way. And so let's do the right cosets this time. And let's go back here. Multiply these same values on the right. So we're going to go take our subgroup and multiply each one of these on the right. And of course, this is the identity, so it's going to be mu1 rho naught, because the identity just always gives the element back. And let's go over here. mu1 rho naught, multiply on the right by row 1. And we'll have to check our table here. So this time we're multiplying row mu1 times row1, mu1 row1 is mu2, and row1 times row0 is row1. And then multiply on the right row2. So we'll have to look at our table again here. This time it's going to be mu1 row2 is mu3, then times the identity row2. And again, we have partitioned the group again. Notice, because we have row1, row0, row2, mu1, mu2, mu3, like that. But notice one thing that we have, notice that we did not get the same cosets, did we? The first one is the same, but notice the other two cosets don't match. In other words, we have a mu2 row1. Over here, there's no mu2 row1, but we have a mu2 row2. And over here, we have a mu3 row2, but no mu3 row2 anywhere over here. So in this case, the left and the right cosets are different. So these are the left cosets, and these are the right cosets. So in this case, so that shows that they're not always going to be the same. And of course, that goes without saying that if the original group was a billion, then obviously the left and right cosets would automatically be the same, because when you're multiplying on the left, it gives you the exact same values you're multiplying on the right. Now, if it's not a billion, I believe you could, in some cases, still have the same left and right cosets, but they would be just generated by different values. In other words, they could ultimately all match, but we wouldn't necessarily have the same member of the group G generating the same coset. They may be kind of mixed. But in any case, so there are cases where the left and right cosets are different, and this is a good example. And we have a theorem that says the order of the cosets of a subgroup, say H, is equal to the order of H. In other words, say AH equals H, and H, and let me maybe write it this way, and HA equals H. Remember, the order of a group are the number of elements in the group. So say for a given A in the group, the order of the left coset is equal to the order of the subgroup H. The order of the right coset is equal to the order of the subgroup H. And we can kind of see that, and it's not a proof, we can kind of see that from the examples that we did before. We had our group, our subgroup H, and like for one case, we had this, and every time we added something to each of the members, we still end up with the same number as the original subgroup. So here we had 6, and then each of these had 6. So if we added 0, it had 6. We added 1, it had 6. Added 2, it had 6, 3, etc. We still have the same number of elements in the coset as we did in the subgroup. And also when we did these over here, once again, H was our subgroup, and it had 2 elements. Then all the left cosets each had 2 elements. All the right cosets each had 2 elements. That's all that's saying. And again, just as a reminder, the order of a group is equal to the number of elements of the group. And also the order of an element. So again, here we have the order of a group. The order of an element let's say A in a group is equal to N, where A to the N is equal to the identity, like this. So again, like say, for example, let me just do a quick example. Let's say if we have the group maybe Z6, then the order of the group of Z6 is obviously 6 has 6 elements. And now let's say the order of, say, 2 so again, under addition mod 6. So the order of 2, again, if you take 2 plus 2 is 4, 2 plus 2 plus 2 is 6, and that's going to be equal to 0 mod 6. And so what did this take 3 times? We had to do this 3 times. So we would say 2 to the 3rd is equal to our identity. So the order of 2 is 3, since we had to do it 3 times to get that. And then the order of, let's say, 3, of course, we just have to take 3 plus 3 to give us 6, and that's 0 mod 6. And so the order of 3 would be 2. So 3. And then, of course, the order of the identity is 1, because you only have to like take the identity just once and you get the identity. So that's just a reminder of orders of groups and of elements in a group. Now, one thing I want to emphasize when talk about the order. So again, the order of an element. Now, again, this number, like in this case, 3, is the smallest number that produces the identity. So when I say this, AN equals E, then the order of this is N, where N is the smallest natural number for which this is true. For example, here, we said that 2 to the 3 was 0 mod 6, but it would also be true. So 2, 3 is equal 0 mod 6. But also, if we were to do it, say, any multiples, let's say if we did it 6 times or 12 times, so let's say we did 2 to the 12, that's also going to be 0 mod 6. But the order is going to be the smallest natural number that produces the identity. So in this case, the order of 2 was equal to 3. Same thing with 3. It had the order of 2, again, because we could also have done, like, say, 3, like, say, to the any multiple, let's say to the 8th power, would also give us 0, but we want the smallest integer that gives us that. So, or the smallest natural number gives that, so the order of 3 would be 2. That's why we picked 3 for this and 2 for the order. And next we come to a very important theorem. Again, the theorem of Lagrange. And let H be a subgroup of a finite group, say G, then the order of H divides the order of G. Or we might say, another way to say it, the order of H is a divisor of the order of G, like this. That's another way to say it. Again, remember, all that means is if we were to divide the order of H into the order of G, we would get a whole number. Or to say that G, another way to say this would be to say that G is a multiple of the order of H. And we can prove this. And so let H be a subset, excuse me, a subgroup of G. And then let the order of H be some integer n. Now we know that the cosets of H partition G therefore for the elements, let me just call them AI in G, say these would be like, let's say all the elements in G, then the order of G is going to be equal to the order of the sum of the orders of the cosets. So let's say these are all the cosets. However, there may be, let's call them, let's say we have M, a total of M members in G. And so we're going to have, and actually, I shouldn't say M members in G, but let's say we'll have a total of M cosets. Because remember, we could have some repeats. So these are just the cosets that don't repeat. We know that they partition G. So that means if we add up the numbers in each of the cosets, we would get G. And for whatever number those is, let's say we have a total of M cosets. And then now remember, each of these, the order of these are equal to the order of H. So remember, we said from the theorem we just gave that the order of each coset is equal to the order of H. However many of these we have. Again, let's say we had M of these. And so there's 1 through M. So there's M of those. And then we had each, then the order of the set H was N. So what we have is the order of G is equal to the order of some M times N, where we set up here where H, the order of H is N. So the order of H is a divisor of the order of G, like that. And so let's take a look at this theorem. And this says every group of prime order is cyclic. Which means it can be generated, remember, just by one element. And so let's do the proof in this. So, so G is a group, and now it's a prime order. So that means, so let's say our group G is a prime order. That means the number of elements in G is equal to P, where P is prime. And now remember from the previous theorem, now any subgroup let's say, let me say for any subgroup H, we just a little while ago that H, the order of H, must divide G, because that was a theorem we just did. The H must divide G, but since the order of G is prime, the only divisors are 1 and that prime number P. Nothing else will divide a prime number. So the only subgroups can be the group with just the identity and G itself. Because if you're gonna have a subgroup that has the same number of elements as the group, and since it has to be a subset, it can only be G itself. Now let A be a member of the group G. Where the order of A and again, of the element A, I'll write like this is not equal to 1. In other words, where A is not the identity. So if it's not the identity, remember we said that any member of a group can generate a cyclic subgroup. And since the only subgroup since the only subgroups that G has are E and G itself. And since we're picking A such that A is not the identity, then it's going to generate a subgroup that's different from the identity. So it must generate G itself. So A is going to be equal to G. And again, we said that this will generate a cyclic subgroup, which is cyclic. So again, the idea is any member of the group G will form a cyclic subgroup. And since it has to be a subgroup and it's not, we picked something that wasn't the identity, so it can't be that this subgroup, it has to be G. And by definition, like I say, by the previous theorem, this will be a cyclic subgroup. So you could further say, one more thing, remember, cyclic subgroups are abelian, so we can say every group of prime order is abelian. Here's another theorem. You call it a theorem or corollary. Say for any finite group G, again, the finite group means a finite number of elements. The order of any element A in G divides the order of G. So for a finite group G, the order of any element G divides the order of G. And so, again, that's very similar to what we had before. And so remember that, let's say, so the order of A, remember that AN equals E for the smallest n in the natural numbers. So in other words, let's say if the order would be the smallest one that would do this, like previously we had the case of 2 in the group Z6, we said its order was 3. And of course, you could also do it 6 times and also get the identity, but we're talking about the smallest value that will give you the identity. So this gives you the identity. And then, so now if you think about the group that this generates, this will generate the group, the subgroup, I should say, A times A times A times A, and then up to the point where you finally have a number of these multiplied, and then you get the identity, and then it repeats itself. So this, so the cyclic group generated by A will have the same order as A itself, because whatever number of times you have to multiply or apply the binary operation to A, whatever number of times it takes to get the identity will also be the number of elements in the subgroup. So the cyclic subgroup generated by A has the same order as A. That is, or we want to write it this way, that's going to have the same order of A. And so now, since any subgroup, the order of any subgroup must divide the order of G then the cyclic subgroup order, which is equal to the order of A, must divide the order of G, like that. So again, the main argument is that the cyclic subgroup generated by A will have the same order of A, and since this cyclic subgroup, that order must divide G, then the order of A must divide G. So another theorem or corollary related to the ones we've just done would say for any finite group G, and any A in G, we have A to the order of G is going to give the identity, like that. And the proof is pretty simple. From what we just proved a minute ago, we proved that the order of A divides the order of G. So, and that implies that the order of G is equal to some M times the order of A for some M in the natural numbers. Then then A to the G is equal to A times M to the A. That's the order of A. And we could rewrite that as A order of A to the M. And so this is the order of A. So by definition, A to the order of A is going to be the identity, and the identity, any power, is going to give you the identity. Then a definition this is a definition of the index of H in G, and let H be a subgroup of a group G. Then the number of left cosets of H in G is the index, which is represented this way, GH of H in G. Some of the problems that we had done in the past, we can go back and look at some of those. For example, we did this problem previously. So we had the group Z12 and the subgroup H, and this had two cosets. And so that's called the index. So the index and of H in G, in this case here, was 2. And then we also did this one. This is our group G, and this is our group H. And in this case, we had 1, 2, 3 left cosets. So in this case, the index of H in G was 3. That's simply all that is, just a definition of how to define that number.